I think you're mute now.
Hello. Can you hear me now?
Yes, yes, we can hear you.
Okay, so can I start?
Yes, yes, please
Yes,
go on.
when you want, yes.
Yes, because I was not. I was in the toilet. I didn't hear nothing. So.
Okay, I just introduced yourself. Don't worry.
Okay.
we are on clock.
Okay. So this is this talk is an example of work that start with some differential equations, motivation, and ends with discrete dynamical systems. This is a joint part of a joint work with Martin Bonner and Claudia Valls that is published in 2019, and a preprint that is about the title Discrete Melnikov functions, that I think is first time that people use in this way this name. You will see. So the talk is, I will explain what is my aim, but I start with some results that are well known for ordinary differential equations, and from these results, I will pass to similar results for different equations. These results start with Riccati, linear and Riccati differential equations, and also the couples the same difference equations. Then the one first main result is about Abel difference equations, but the problem is that Abel difference equations is not so clear what they are. So I will introduce these Abel difference equations. And finally, I will use something about some results about discrete Melnikov functions. And the goal of the talk is only to find examples of periodic solutions, nothing more. There is no dynamics, global dynamics at all. So only for some classes of Riccati or Abel difference equations, how to be sure that these difference equations has a several number of periodic orbits. So yeah, you will see in a moment. So this is what I have explained. I will talk about linear, Riccati, and Abel differential and difference equations. So I start with known results for ordinary differential equations. This what is here all the situation is we study one-dimensional first ordinary differential equations, non-autonomous. You see that these differential equations are polynomial in X, and all the functions A0, A1, the coefficients of the polynomial part are omega periodic functions. And we are interested in the study the number of periodic solutions, also omega periodic solutions of this one-dimensional non-autonomous differential equation. This equation, when the degree changes, has different names, so you know, you will see now, but n1 is linear, n equal 2 are the so famous Riccati, and n equals 3 are the Abel, and n bigger than 3 will not be touched in this talk, but it's generalized Abel equation. And the main question is, which is the number, not the number of periodic solutions, because it's possible to have continuum of periodic solutions, but the number of isolated omega periodic solutions. Informally, people call these limit cycles of these equations. Although limit cycles is a concept for planar autonomous, here also people omega periodic solutions of omega periodic differential equations in this setting that are isolated as a periodic solution that call it limit cycles. So this is what I will study. The main results start in the 60s and 70s about these equations. So what is known about for differential equations of this type? For linear is very easy. This is an exercise in any first course of differential equation that these differential equations here a0 plus a1x tx and nothing more have at most one limit cycle, let's say. This is the maximum. For when n is 2, here a0, a1, and a2 x squared, the Riccati case, the maximum number is 2, and there are several proofs of this fact. Everybody knows you assume that you have one periodic solution, then you make the usual changes of variables, and you arrive to a linear, and then you have the one of the linear and the one of the one that you have used for the change, and you have two for the Riccati. For Abel equations, mathematical community had a big surprise because Linz in the 80s proved that when you put here a polynomial of degree 3 in X, this is the classical Abel equation studied by Abel. For other purposes, let's say Abel studied these equations for studying integrability of equations, not for this problem of periodic solutions, but the name is because he studied these equations. Then the surprise is that for any m, you have one of these equations that has at least m limit cycles. This was a big surprise because at that time in the 70s, people start to find, at the beginning, people thought about 3, then someone find 5, then other 7, and after some time, Linz proved that there is no upper bound. As far as I know, there are no examples with infinitely many. I think that it should exist one given equation with infinitely many isolated periodic solutions, but for the moment, people only has proved this. And also the same result, this is not because all these periodic orbits are hyperbolic, and then for bigger degree, no problem to get more, or also any arbitrary number, because you put the cubic Abel equation, and then you put epsilon x to the n, simple constant perturbation, and all the finitely many that you have, because it is proved at the same proof that they are hyperbolic, they remain. So this is not important. This is a easy corollary in the same paper. So this was known when we started the problem. And what about we tried to study similar problems, but for difference equations. So what is for difference equations? I need there are for linear there are definitions. For Riccati, some people uses several different definitions, and for Abel, definitively there is no natural notion for Abel difference equations. So we choose the way of making Martin Bonner. Probably you know him. He works many in time scales, but we use here time scales only for motivation for the definition, not all this stuff. Only a few words that when you take the reals, there is this common notation. The derivative you call this operator name the increment. This is another f super sigma subnotation, and the integral is the usual integral. These are notations for time scales. The left hand side and the right hand side are the usual notation. But when you take the time scales that I am not even defining what is time scales, the equivalent to the derivative is the increment, the equivalent to the f sigma. This called sometimes the next one is simple, the next one in the discrete sense. Here, because let's say you have a continuum, the next one is the same, you have no change, but here you make a jump of one unity. And the integral, of course, is the discrete sum, the finite sum of this in this form. So we use this trick. You take this Abel differential equation, we transform this as a time scales equation. You see here x prime is x delta because of this relation. Here we keep, but here the x squared we change because these are different. Are the reals because we are making usual derivative. We change one by x and the other by next x. That for this for continuous is the same. And here we choose to put two usual x and one next. But now this is an equation in the time scale setting that has other examples, but I don't care about this. Now I write this because I have started with the usual Abel differential equation. Here I pass to a time scales equation, whatever it means, and this is only a formal process. And next step, I change by my dictionary. This is the increment operation. Here is the same, but here you see x sigma is xn, and the next one here ddt is dn sequence. Here x squared is the same, and here is the next one. And of course, from here you can. I have put it here only one sigma because in this way I can make from here I can make I can get xn plus 1 in terms of xn. So in short, this is the Abel differential equation, and this will be my definition of Abel difference equations. So I will consider these difference equations, the ones in the top, and here the linear case, of course, for differential equation, and this is the linear for difference equations. The Riccati is this one for differential equation, and this one for difference equations, and the Abel is this one, and this is the right hand side. This is the one that I have here, this quotient. This is my definition of Abel difference equations. Here only some few words because the right two difference equations are well known. For instance, this one, when the functions a and bn are periodic, recurrent sequences that are periodic, this is the problem that we will be interested. But this problem is motivated, this one here, for the biological models. For instance, this equation, this xn plus 1 equal this quotient, is called Beverton-Hall model for populations. And here, when AN, BN, CN, DN are sequences that are periodic, this is, if for instance they are 4 periodic, this means that each season of the year, like winter, summer, and all these, the 4 seasons, if you take here 4 seasons, then this corresponds to take 4 periodic sequences here, one for these ones, and the number of study these periodic difference equations is the so-called Beverton-Hall model. And you can have also other periods here, the number of periods. And for Abel difference equations, here's the differential equation, here's the difference equations. So our main results here is that it happens more or less the same that for differential equations. Again, this is for folklore. Again, the linear ones, that means nothing in the denominator. There's linear difference equations. They have the maximum number of isolated omega periodic solutions is 1, like in differential equations. For Riccati, also is well known that the maximum number is 2. And also this is our main first result, that when you take omega periodic Abel difference equations, meaning that you have here En is not identically 0, then for any M, but here in the other case was unbounded, but for any M smaller than the period of the AN, BN, CN, and DN, I call omega, it's a strange name, but here is a natural number, for any period smaller than this m, you have these examples of these difference equations with this number of isolated periodic solutions. So at this point, maybe some people can start thinking that just when you have a finite, and you have here periodic AN, BN, CN, DN, these are periodic sequences with some period, and you want to find periodic solutions of this, you only need to make composition of several maps and solve the system. And this is true, but computationally, in general, is not easy at all. Solve the systems and study the number of solutions and to prove that are isolated. So in this talk, what I prove is how to get examples with this, especially the third case, how to prove this in some dynamical systems point of view. Let's say taking some case that is more or less integrable, that has continua of periodic solutions, and then make a perturbation of this system in order to have this number of isolated periodic solutions. So, but before passing to the Abel case, it is one of the main results of the talk. I will say a few words about Riccati, the Riccati case, because there is an open problem here that maybe not all people knows. I make some comments about the Riccati differential and difference equations. This is also part of known results, but I think it's interesting to know. In this case, it's curious that the case of difference equations is much easier than the case of differential equations. Let me explain why. When you have this kind of difference equations, this is where all functions all sequences A, B, C, and D are omega periodic. Omega is a subnatural number. Everybody that has found these Möbius maps here knows that there is some nice algebra here. If you define the matrices in this way, where you have here A, B, C, D, but are written in this way, A, B, C, D, and you make the composition of these matrices, the usual product of the matrices, you get this big matrix that is the product of all the omega matrices that you have here, that are the ones that are give the difference equations. And just to find the periodic solutions of this is simple, is a problem of solving this quadratic equation. And because this is rho is the initial condition, because these are different equations of first order, you have a rho, the initial condition, and here is the condition to have a periodic solution. So you have a quadratic equation, and for this reason you have at most two isolated solutions that are the zeros of this quadratic equation. So nothing difficult here. This is because the proof in the folklore that 2 is the maximum number of isolated periodic solutions for these Riccati difference equations. For differential equations, the proof is quite similar. You have this differential equation. Rho is again the initial condition, and you want to solve this differential equation. What happens here, this is another motivation, or another reason for the name, that the flow of these differential equations is also a Möbius map. The flow of this differential equation, with here A, B, C are these letters, is this this is the flow at time omega of this differential equation. Is also a Möbius map. But this A, B, C, D are not very easy to be obtained from this A, B, C, because this A, B, C, D only can be obtained very easy from the small a, b, and c when this equation has an explicit solution. but it's very difficult. Many Riccati differential equations have no explicit solutions. So in general, even it is very easy to prove that this differential equation has at most 2 limit cycles. The proof is just simply take the return map, this one, and import that you have a fixed point and you have a quadratic equation, so at most 2. But the problem is that these A, B, C, and D are not explicitly obtained from this a small b, and small c. So you have there is this, and this is an open problem in general, that given a Riccati differential equation, give effective criteria to know if this equation has 2, 1, or 0 isolated omega periodic solutions. While in the other case, in this case, is purely algebraic. You take these sequences that are periodic, you construct these matrices, you multiply the matrices, and you solve this quadratic equation. These are the periodic solutions. Here, formally looks similar, but the problem is this A, B, C, D, there is no known way to get this number explicit. So this is what I wanted to say about Riccati. And now I go to the case of Abel. For the Abel, what I want to prove is that there is no upper bound for the number of periodic orbits of the period that have, I only study periodic orbits that have exactly the period of the difference equation, not the general problem of other periods. This is very concrete problem. To have this proof, I try to prove this part here that is not is possible to read, but this is for difference equations. But to have to get a proof for the case of difference equations, what I will do is to mimic the proof that the Linz proof for ordinary differential equations. This is not exactly as Linz proved, but the idea is the same. How I do this is how to prove that another. I will prove now the old result of the 80s that Linz, that omega periodic Abel differential equations have no upper bound for the number of isolated periodic solutions of period omega. So the idea is like goes back to Poincaré, is just to you take a simple, very simple differential equation where you have continua of periodic solutions. This will be this Riccati, only without the epsilon, x prime equals ct x squared, and then you add a perturbation. This perturbation makes the equation of Abel type. We don't need to put linear and degree 1 term in x. Just but how but I have here, this is a proof where I have removed all the noise, and is the easiest. I like to say that is maybe the easiest way to prove Linz result. Just now you take, these are the Abel differential equation when epsilon is different from 0. I simply take this one and this change of variables. With this change of variables, the inverse one, just y dot, this first part is y dot is this one. So in the y variable is simply y prime equals minus c of t minus epsilon. In this way is I use the Poincaré perturbation method. This is if I am away from 0, this 0 in y is the infinity in x, so no problem because I am in some compact region. And then I look for a solution of this equation that has some small parameter here. This is y prime minus ct epsilon, this function. I write the solution like a principal part, a first order. These are I will find the first order variational equations of this differential equation, and the initial conditions as are that at the beginning you have the initial condition is rho, and this perturbation has the value is 0. So what I have to solve, I plug this equation in this differential equation, in this special solution, and I simply got that u prime must be minus c of t with this initial condition, and b prime is the second part, is just must be minus d of t over u of t, where u is the solution of the first part. This is the unperturbed part, and here is the first order. So here is, I have repeated here, this is the unperturbed part, and here is the first order variational equation. But from the first differential equation, the solution is simply this one. I use here the notation, the small c, the primitive. So I have that the unperturbed solution are simply these ones. So from this, I can replace u because I have already this in terms of the solutions. I replace the u in the differential equation of the first order variational equation, and I have that the solutions of the perturbed Abel differential equation in the y variable is this unperturbed part plus epsilon, this part here that is not explicit, is some integral, plus second order terms. So this is, I repeat here, again, this is again the same. I have repeated here. You have here the differential equation, and here the solution. This is the Poincare perturbation method. Now, I want to have periodic solutions of this perturbed differential equation. The first thing that I need is the unperturbed case is full of periodic solutions. So to get this, I simply impose that the integral, this c, when I evaluate this at omega, that is the period, I need that the unperturbed part gives a continuum of periodic solutions. So the unperturbed part, I need that c omega must be 0. So this is c omega is the complete integral of c, the integral between 0 and omega of small c of s dds. So from this equation, I can define it, the Melnikov function as this function here. Remember that d was a function that was in the differential equation here. Sorry, d is this function, c this one. So I define the Melnikov function as the integral between 0 and the period of d of s. This is one of the functions appearing in the differential equation. And this capital C is the primitive of small c, that is the other function in the of the Abel differential equation. So this is the Melnikov function. And this Melnikov function, when you find the solution of the differential equation at time omega, you get rho minus c omega, that is this is precisely 0, minus here epsilon of the Melnikov function. So it's clear by the implicit function theorem that when you have simple zeros of this function, if for some rho this function has a simple 0, then by the implicit function theorem you have a solution, an initial condition of periodic solutions for the differential equation. This is the theorem. When you have this differential equation under this condition, that is the condition that the unperturbed system is full of periodic orbits, then each simple 0 of this function, this is the the Melnikov function, gives for epsilon small enough an isolated omega periodic orbit of the differential equation. This is the proof of a free version of the proof of Linz. So now this is the method. Now I need the example. The example is just some computations that I will skip. You need to put some example, concrete example. the idea of Linz was put C of t simple cosinus. You put a cosinus here of this shape, omega periodic, and this function, of course, has integral 0. This is the unperturbed system that is full of periodic solutions, full meaning not the full plane, but an open set of periodic solutions. And that then put here a trigonometric polynomial in sinus, a huge trigonometric polynomial degree with m+1 terms. This is a periodic function here. And then when you have here, you need to prove that you can choose the beta j such that the function m that has the number of zeros that you want, that is m. But it's very easy because this function m, remember this function m is just here a trigonometric polynomial, here a sinus, so you can make all these computations almost explicit, and you have an example with the number of zeros that you wish, that is this m. It seems that very easy, but was a surprise at the same moment, because if you try to do all this stuff with Riccati equations, you never succeed. For Riccati, you can take a simple example where a linear case where you have a continuum of periodic orbits and then make a perturbation. But for Riccati, it doesn't matter the perturbation, the number of parameters, what you wish, the maximum number of zeros is 2. On the other hand, here is very different because here you can have examples with m. Now, some people is trying to have upper bounds for these equations when you have in general for this differential equation, the one from the beginning, when C and D are trigonometric polynomials of given degrees, people is trying to get upper bounds for the number of limit cycles but this method of Poincaré only gives lower bounds, but no upper bounds at all. And this problem, I would like to say that is as difficult as Hilbert's 16th problem. So here, for the moment, no way of solving this. But now we will see in a moment that you can do the same for difference equations. Let's see a moment what happens here. Now, this is one of the results of the talk. This is published in the paper of 2 years ago. You take this Abel difference equations and you take here, you put the epsilon, the perturbation. Remember, when epsilon is 0, you have here what Beverton Hall type model, or in other words, a Riccati difference equation. When epsilon is 0, you have here, it's very easy to study this case, and I make a perturbation. So I do the same. Here, I make the same change of variables because we adapt the proof in the other case to get here something similar. So I have here, I made the change and I arrive to something that reminds me the other case. And then I use also the same variational methods. I try to find the solution of these different equations, like some first order part, 0 order part, some other sequence Bn of first order perturbation, and initial conditions the same, and then making here, plugging this in this different equation and making an order arrangement. I have the first difference equation and the second difference equation, now very simple. You remember the other ones were exactly the same. U prime equals minus C. So here, this is the increment, U prime is the same. Here I repeat the equations, these are the same. The unperturbed part, the first order perturbed part. Now I have to solve here, but again here you can solve this. This is the solution of the unperturbed part. Looks like the other one looks U of t equal rho minus the C of t. So it's the same here. And also because I have this U, you can replace this one here, and you had here the B. The B, you can solve the B similarly, and I have here the solution. Maybe most of you already see here the Melnikov function. Now is this part here. Again, I continue here. In short, I have this was after the change of variable, the Abel difference equation. This was the solution. And now, if I want to have periodic solutions of period the omega, because I call omega because it's the same name than the other case, this omega is the period, I only need to replace here, and the condition is that this C omega must be 0 in order to have the unperturbed part has a continuum of periodic solutions. So I can define the Melnikov function. We have not found this definition in anywhere. This is our definition. This is the Melnikov function, and again the same proof. By the implicit function theorem, you can prove this result. If you take this difference equation and you take this Cn is an omega periodic sequence such that the total sum is 0, then each simple 0 of this function here, that is the Melnikov integral, let's say, gives an omega periodic of the difference equation. Is again the same. So this is the theorem. This is again the same statement, but now I have to prove to construct the example with an arbitrary number. So what I do here is just take a very simple case. I take this Cn like any sequence that the sum is 0 because the unperturbed part is omega periodic, and I have to prove that the Melnikov function, that is this sum here, has the number of zeros that I wish. So this is exactly, I have omega functions here, and I need to prove, because this is our goal. Before was some integral with sinus, cosinus. Here is different, that this function, as a function of rho, has some number of zeros. But the point here we use a different tool. There is a general theory that is the complete ECT systems that gives a method to know given n functions how like think for a moment that these are as a polynomial. This is f0, x to 0, x to power 1, x to power n minus 1. These are a polynomial of degree n minus 1. Everybody knows that this polynomial has at most n minus 1 zeros, and you can choose the coefficients in the way that you wish that the zeros are in the place that you desire. Here is for an arbitrary number of also n functions. I want to choose the coefficients. Here my functions are these functions 1 over rho minus cj. And I want to choose the dj's that are the perturbations such that this function has the zeros that I wish. So, but the theory say if you want to do this, if these functions satisfy that the Wronskians of the functions are different from 0, then you can do this. This is the well-known theory, call it Chebyshev systems theory. But in this case, it's very easy because this determinant of this is quite similar to van der Monde determinant. So you can compute and prove that you can put the zeros where you wish. And you only can put as many zeros as functions minus 1. This is like happens in polynomials. Degree n polynomial, n zeros. Here is degree n minus 1 because I have chosen stop and n minus 1. So n minus 1 zeros is the same. And so this is the proof of this result. The last part of the talk is a little more technical because all this was like the starting part This was our first work, and now we saw that this can be applied to other situations. The first situation, I only say a few words on the first, is that in all the time scale setting, you can do the same, but I don't want to continue in this direction, but only take a look to this transparency. You have here is the differential equation, here is the solution. But in general, you have here, this is the difference equation, and here is the solution. This is the reason why time scales was born. So you, at some moment, you can think that here you have something that is known in differential equations, but here is not mejor. What people did in time scales many times is put in the proof of two apparently different things in the same notation. Here, this was not proved. So we have used the idea of differential equations to get the one of discrete dynamical systems. This is quite natural. And now from here, if someone wishes, can have some kind of result for time scales. I even don't care much in other time scales, but these kind of theorems can be proved. You take this is called an Abel dynamic equations, where here is something that I don't have defined it well. This is like the derivative of the increment here, but I mean in an abstract setting. So this kind of Abel dynamic difference equations are called, that include the differential difference and other type of equations, and meet some Abel differential equations where this integral here, this increment means that this a different integration is maybe the usual integration for differential equations, the sum for this for discrete for differential equations of other ways of making computations in other time scales. I repeat that I have not followed this direction. I only wanted to say some words about this here. And the last part is a lot. I will pass this because we start to be tired and this is more technical. In few words, is that you can do the same in the discrete dynamical systems stuff for in any dimensions. So you don't take, you simply take these autonomous difference equations. These are not different, and now are discrete dynamical systems. This, I erase the omega because I really don't like much that is omega periodic. This omega was because for differential equations was real, for difference equations was a natural number. We decided to put omega, but here I changed the notation. I put simply this an n periodic sequence of difference equations. Of course, to find periodic solutions of this, of period n, is simply to take the composition of the maps. I call this composition F0. Here is the composition of the F0, then F1, then F2, then F3, until Fn minus 1. And this is the flow, just simply by definition. And I want to have a method to study the number of periodic solutions of this, and to see that there are many periodic solutions for these concrete cases that is not force brute. That force brute is just put here equal rho, where rho is a point in RD, and solve this. So the point is that you can do the same. You can take, if you take, this is in general, this is in RD, this iteration. Here you have Fn, Gn, Hn are periodic, and then are n periodic, all these sequences of maps, Fn, Gn, Hn, and then you can try to find a solution of this form, that is unperturbed part, that is the solution of the first part, that is the composition of the F. Here you have the first order variational equation to find this. Here the third order variational equation. And then when you have solved this, you have found this, then you can define the first order Melnikov function, like this function evaluated at the period. and the same here. But in short, I have this. This is the result that when you have here the first one is like the sum, a sum of something where you have here is the part of the solution of the unperturbed part that you know that is full of periodic orbits, and here apply it to the perturbation. And you can do with some more work something similar for the second order Melnikov function. Even I don't care about this. Just I want to say that, for instance, for differential equations, you can do the same also, and this is was known. This is the called first Melnikov function in any dimension, and can be written in this form. And here we have something similar, that is this function, that is a function in d variables, and the isolated zeros of this function give periodic solutions of period n of the perturbed system. Here the proof is just you put in the differential equations. You need a little more of work because you are in differential equations. I skip this part because it's just simply uh, solving linear equations as usual for variational equations. But here are linear equations, systems of linear equations. So you see, I only show you because I don't, because I have written here. And finally, you have the proof that the function m1 is like in the example as discrete sum. Like to see a concrete examples, just to almost to end. You have here I write an example for difference equation. Here I have a difference equation like this one, xn plus 2 equal. This can be thought as a map from R2 into R2, this difference equation. This is the unperturbed part, and I take an unperturbed part that is periodic, meaning that all solutions are periodic. This is them, and then I make a perturbation with the same period here that the solutions. If you want to see examples of this, for instance, if you put here this function, so xn plus 2 equal 1 over xn, this unperturbed part is globally 4 periodic. If you put here this 1, this is more famous, the 5, you put here xn plus 2 equal 1 plus xn plus 1 over xn, this unperturbed part is globally 5 periodic. So this means that if I put here this unperturbed part and then I perturb with a 5 periodic solution, I have a formula to know which are to know periodic solutions of the same period, 5 of these different equations. For instance, in one example, if I take this concrete equation, this is a concrete equation. Here I have this perturbation. So if I want to find periodic solutions isolated for these different equations of period 3, because this without the epsilon is globally 3 periodic, I get a Melnikov function that is this function from R2 into R2 that depends on the perturbation. This is a concrete two variable function, and the isolated zeros of this function give rise to periodic orbits that are periodic for the unperturbed system. From them bifurcate some isolated periodic orbits of the perturbed differential equation. This difference equation. With this, I think that I will end. Just I end also like with a flower, but this flower is, I even don't know the name, but I only know that this is in my hometown. And I liked from I was a child. In the forest, there are very few flowers here in El Valles, near Barcelona, and this is one that I like. So thank you very much for your attention.
Thank you, Armengol, for your nice talk. And